Okay, so we looked at two methods finding minimum spanning trees, and I spoke at length at one stage about the fact that the minimum spanning tree is not the same as the shortest path, and that you're going to have to be very, very careful with it. And then, so we had worked out shortest paths with non-weighted matrices, in other words, matrices where we could just say all the edges are 1 and go from there. So you have to be thinking about the idea of, is there an algorithm, particularly when you have a weighted matrix, so that you can find the shortest path? The answer is obviously yes. We're going to be covering one of them, but the idea behind it is going to show that there are some connections between them. So the one we're looking at is called Dijkstra, and Dijkstra is very, very similar to Prim. Now remember that Prim was very, very similar to the shortest path algorithms, and that's actually why Dijkstra is similar to Prim and, that whole approach. So a reminder about Prim. So remember, Prim took an edge of minimum weight and you placed it in your tree, and then you looked at the nodes adjacent to the ones that were in the tree already. So you looked at the vertices adjacent to the vertices that were already in the tree, and you selected the edge of minimum weight there, and you went on that approach. So Dijkstra is going to follow a similar style of pattern in regards to that. So you will again look at the case of you select a minimum weight vertex. Obviously, in this case, because you're looking at shortest path, you would be like, I want to start at vertex A or vertex D or whatever, and that will be the one that you start your tree off with. Then you'll go from there and searching, and you're going to obviously search from that vertex that's activated in your tree all the adjacent vertices. In other words, you'll look at the adjacent edges weights and select the minimum weight, and that will be the one that you're going to pretty much add to it. Okay, but the idea behind this is we're also going to add some extra information. So what we're going to do is we're going to have a situation where we have a starting vertex and a starting root essentially, and we're going to give it a potential of 0. So much like with Moore's breadth first search, we had that level of 0. That's what we're going to do here. But what we're going to do that's different to Moore's breadth first search is we're going to update all our other vertices in our graph to a temporary label of infinity. So we're saying so with this, it's a temporary label of infinity. In other words, we can't reach it yet. And when we perform the search, we're obviously going to perform the search in such a way that we're going to end up selecting the minimum weight to get to that vertex. So we use infinity because obviously infinity is gigantically large. Any edge weight, that exists. Otherwise, we'll replace that infinity symbol. And what happens is we have the temporary labels, and then we're going to have the permanent labels. And the permanent label is going to be that minimum length, that shortest length. So let's actually write out the process. So we have a starting vertex that we start off with, given a starting vertex of a potential of 0. And that's because if you're at that vertex, to get to that vertex, you don't really have to go anywhere. Okay, and all the other vertices in your graph are going to get a temporary label of infinity. You're going to see it now when we do an example of what exactly I'm talking about there, and it's going to become way, way clearer, but let's just get through this. You can always skip ahead. And all other vertices, a temporary label of infinity. Okay. Then we're going to look at the vertex that has received the most recent potential. In other words, the one that's been updated to the shortest distance, as in there's no other distances that could possibly be shorter to that vertex. So, from the vertex with the most recent potential. So if you were just starting out, that would be from your root vertex. You're going to look at every vertice adjacent to this one, and you're going to calculate the potential plus the weight of that incident edge, or the edge, that adjacent edge to that vertice. And then you're going to replace your temporary label with an updated version dependent on the rule. And the rule is obviously going to be, well, if the potential of that vertex plus the weight is less than the temporary label, you update the temporary label. Because remember, the whole goal here is to find a minimum amount. So, from the vertex with the most, I don't think you can read my handwriting, that's supposed to be most recent potential, we're going to look at, firstly, every adjacent vertex. And we're going to update or not update, leave as is, their temporary labels. So we're going to update it as we have the potential plus the weight of that incident edge. And we update it to this new one if this one is less than the temporary label. Okay. So you update if this situation occurs, and you obviously update with that potential and the weight of the incident edge. So you replace your temporary label. That should say label. I don't think my handwriting is very clear. You replace your temporary label if the potential plus the weight of the incident edge is less than the temporary label that it is currently. Okay, then you look at all the temporary labels of the adjacent vertices, and you make the smallest temporary label into the next potential. So previously we had active and inactive. So here we have the situation, we refer to it as potential, and then we have the temporaries. Okay, so make the smallest temporary label the new potential. And we repeat this process here until you basically get to the end. So if you were looking for the shortest path between vertex A and vertex B, you would continue until you get a potential value at vertex B. Or if you were going from vertex A to vertex F, you would repeat until F has a potential associated with it. In other words, once it has a solid number. Okay, so you repeat until the vertex you're trying to reach has a potential. Then it's a case of, so remember the whole idea behind Dijkstra is to find the shortest path. Yeah, you've now actually gotten the distance to the path, the distance of the path. But you can get the path now from this because you can backtrace. You can, go through your potentials and find your path by just having a graph of all the potentials. So we're going to look at that, and we're going to look at that by basically looking at examples, because I feel it's a lot clearer if you just look at your example versus just talking about it or writing down words relating to it. So let's jump straight into an example. Okay, so there we have a graph and it has a bunch of weights attached to it, and I'm going to be like, let's find the shortest path between D from A to F. Now, you could look at it and immediately see that it's actually, A to D to F, but we're going to follow Dijkstra's algorithm in this approach. So for Dijkstra's algorithm, we first take our root and give it a potential of 0. And what I'm going to do two approaches. I'm going to do it on the graph, and I'm going to do it in a table just so you can see the difference. So if we have a table, what we have is we write down all our vertices, A, B, C, D, E, F, okay? And then we start the approach. And when we do this, we're going to have, okay, A is the beginning. It has a potential of 0. So there is a potential of 0, there is a potential of 0. All the others get a temporary label of infinity. So this gets infinity, this gets infinity, this gets infinity, this gets infinity, and this gets infinity. So on your table, it would be something like this. Okay. Next up, you don't actually have to have that line, but next up, you'd now look at all the vertices adjacent to A and update their temporary labels. So you'll take the temporary label of A plus the weight of the incident edge gives you your new temporary label, or the one that you'll compare with the current temporary label to see if it needs to be updated or not. So in this case, you'd have 0 plus 7. That's going to give us 7. And obviously 7 is less than infinity. So B is going to be updated to 7. So B is going to be updated to 7. Okay, and you're going to go again through the approach. You'll have from A to E, because E is also adjacent, you'd have your 0 plus your 3, which gives you your 3. And obviously 3 is smaller than infinity. So we update our temporary label of E. And we do the same for D. So again, we're looking at all the vertices adjacent to A, and we updating their temporary labels or leaving them as is, depending on the rules of how we follow this approach. So we have again 0 plus 1 gives us 1, and that is obviously going to update that temporary label. So D's temporary label is now 1. Okay, now we look at all the temporary labels that we just looked at, and we take the one with the lowest value, and we make that one the potential. So this is now actually a potential. It's 1. So instead of being a temporary label, it is 1. Now you're going to look at all the vertices adjacent to D and follow that same approach. So, and yes, I'm not going to jump straight to F. I'm going to do it a little about turn here. We have 1 plus 1 gives us 2. So 2 is less than 3. So the temporary label of E now gets updated to 2. Okay, then we look at the other one, and we have the situation of 1 plus 3 gives us 4. So 4 is obviously smaller than infinity, so we update the temporary label of F. Now the thing is, we were looking for the shortest distance from A to F, so we could kind of actually stop here already. So, but technically not entirely. Because remember, your rules did say, and the reason we could stop is because F is only attached to D, but the rules of Dijkstra's algorithm did say one very, very specific thing. It said you only stop once that temporary label is a potential label. We have not done that yet, so let's continue on. So again, we look now at your temporary labels and we select the minimum. So in this case, it's E, which is 2, and we make that one the new potential. So we have this is 2 as the new potential. Then we're going to look at all the vertices adjacent to E and go from there. So all the vertices adjacent to E, so we have B, so let's actually have a look at that. So our next layer, let's use purple. So we have 2 plus 3 is equal to 5. Is 5 less than 7? Yes, so we update this one here to 5. So we've updated this one to 5. You should do it in a neat little order situation, but again, I'm just throwing this on the page. So we've updated B to 5, and we move on. Okay, we don't go back to A because A is set, it's got square brackets, it's a potential, it's fully active, you can't do anything with it now. We move on and we have 2 plus 11 gives us 13. 13 is definitely smaller than infinity, so we can update that one. Okay, so we've updated that one. Where else can we go? We can't go back to D because D is got its potential, so we're kind of done. Next, we look at all our temporary labels and we look for the one that is, and again, you're looking at the smallest temporary label. So in this case, it is F, which is 4. So you make that one potential. So that is now potential. So now we can actually stop according to our Dijkstra's algorithm. So we can say D A to F is equal to 4. Okay. So let's do it again. Let's actually neaten this up. Let's neaten the table up to show ways to represent it so that we can actually do it for all of the situations. But before we continue on, now you know that the shortest path from A to F is 4. What is that path? And what you can do to find that path is you can actually go back with the information that you have. So I'm just going to clean up my graph a bit. Take away information that you wouldn't necessarily have, to show how you can go backwards. I took a little bit too much information away there. E was 2. Okay, so we start with F and we go 4 minus 3, and that gives us the 1. So we know we go from F to D. Now, if we had more adjacent vertices to F, we would have had to look for all those cases. But we know that here it goes to D. So we have a situation of F and D. Then what we would do is we look at all the adjacent vertices to D. So here we have 1 minus 1 gives us 0. That is not equivalent to that potential. So we know we didn't actually follow that path or that direction. But here we have 1 minus 1 gives us the 0. It's the same as that one's potential. So we know we go from D to A. And then we know that our path from A to F is just the reversal of this. So it is A, D, F. Okay, so you can find the length of the shortest path, and also given the potentials and the weights, you can find exactly what path it is. But again, we're going to do some more examples to clear it up. Okay, we're going to use the exact same graph, but now we're going to look for the shortest path length between B and F. So we're looking for D, B, and F. So we start off with B, we activate B, we set it to be a potential of 0, and we move on from there. So again with the table, you can say A, B, C, D, E, F. And I'm going to just show you the way to the table just so that you don't have to, remember when you backtrack and so on, here I do it so that you actually keep track of it the entire time. Okay, so step 1, you give that one 0, all the others are infinity. Right. Oh, I forgot a very important factor. I'm starting at B, so my A isn't 0, my B is 0. Okay, so that is our potential of 0. Everything else is infinity. Okay, let's just do that. All the infinities are there. Then we are going to look at all the vertices adjacent to B and update their temporary labels if necessary. So let's go through that approach. So B is adjacent to A. We update this temporary label by saying 0 plus the weight, which is 7. So this becomes 7. And this one becomes 3. 0 plus 3, 3. And we know that both of those are less than infinity. So we update them. So that's what we're going to do here on the actual table grid as well. So we have A is 7, E is 3. And the rest just chill as they are at the moment. But now what we've done is we can also keep track of what we're doing. So we know where this is from B to A, and this is also from B to A. So that's just keeping track of where we're going. Next, we look at all the adjacent vertices there, all the temporary labels, and we make the smallest one the potential. So we update this one to be the potential. So we update this one to be the potential, so we have 3 chilling over there. Okay. Moving on, we now have, 3 as our potential, so we look at all the vertices adjacent to E and update their temporary labels. So let's go through this approach. So E is adjacent to C, so we have 3 plus 11, which gives us 14. So here this is 14. We update this one to 14. Shouldn't actually be using purple, but let's just go with it. Okay, then we have 3 plus 3 gives us 6. 6 is smaller than 7, so that's a better approach. So this one gets updated. But because we now have an updated situation, we can look at our path and we say, well, we actually had BA to E. Here we had hold on. Here we had B to E, sorry. Made a mistake there. There we had B to E, right? And we to get that 3. Now we've updated A utilizing E, which means our path is no longer B to A. It is whatever was over here plus now going to that A. So this gets updated. So you don't have to do this part. This is just for those, you know, who want to keep track so they don't have to do this again. So you have B, E, A now as the new pathway to get to that 6. So in other words, I'm already doing what path it is. I'm labeling it as I go. You don't have to do that. That's just an extra piece. Okay, we go back to E. D is also adjacent to E, so we need to check that one out. So we have 3 plus 1, which is 4. So D gets updated to 4. Are there any other vertices adjacent to E which do not have potentials already? No, so we're done. So now we look at all of them and go, which one has the lowest potential? In this case, it is your A, so we have 6 becoming our potential. Don't forget, I should have put that there. Okay, so then we have 6. Okay, so now A is our potential. We look at all its adjacent vertices and we update to C. So A, we have, let's choose a different color. We have 6 plus 1 is 7. And that is not smaller than 4. So we actually leave D as is. Are there any other vertices adjacent to A which don't have potentials? No, so we're done. So at that moment in time, we're done, we're over. One of the things I have not done, which I was saying that you should do, was, you know, do all the pathways. So in this case, to get D to 4, we went B, E, D. And to get C to 14, we had B, E, C. You should be doing this at the same time as you put everything down. My bad, I tend to forget, but then I go back from there. Okay, so now again, we are selecting the one of the lowest temporary value, which happens to be D. So D becomes our new potential. So it becomes 4. And I just want to make sure that everything is in neater order. So this was updated to 4, then it became 4. Notice I'm going from left to right here in the way that I write this down. So now we look at all the vertices adjacent to D and update their potential accordingly. So if we go ahead and do that, we have the only one that doesn't have a potential value is F. So we have 4 plus 3, that gives us 7. 7 is obviously smaller than infinity, so we update that infinity to 7. And we update that infinity to 7, and we remember that we went, so we take exactly from D, we have B, E, D, and then we add the F. Okay, now again we look for the lowest, and we make that one the potential. So in this case, it happens to be F. So this is 7. So we can actually stop at this point. Okay, so we already have the distance from B to F. The shortest distance is 7. So we already have this answer. And the nice thing is, the way that I did this with tracking the path, we already have the path as B, E, D, F. However, if you didn't have that, you would have had to go back. And now if you went back and you didn't necessarily have all this information, let's just rub all this out. So you would have only had the potentials, and that's about it. So you wouldn't have all this in between aspects. So you would have said, okay, 7 minus 3 gives us 4. Whichever ones, so if the 4 matches the potential of D, which is 4, then you know you traveled from D to F. So you write that down, FD. Then you would have to go from D and look at the different cases. So you say 4 minus 1 is 3. That does not match the potential of your A, so you did not travel along the route of touching A or going past A. But you can also say 4 minus 1 here is equal to 3. The potential of E is 3, so you definitely did cross E's path here because the potential is the same as what you worked out there. So you had your E. Then you would have been at E, and then you would have to go through all the adjacent vertices again to test out. So we have 3 minus 3. That gives us 0. That is not the potential of A, so you didn't go in that direction. You could also test out 3 minus 11. That is obviously a negative number. You did not go in that direction. And then you could say 3 minus 3 is equal to 0. That 0 matches the potential of B, so you did go in that direction. So when it matches the potential, you go in that direction. And then you would have had FDEB, and you would have just switched it around to get BEDF as the path that you took to get from B to F, which is the shortest path. Okay, so for our final example, we're going to use the same graph, but now we're going to look at D, A to C. So we want the shortest path from A to C. So A is the one we start off with the potential equal to 0, and I'm going to do these separately now. I'm going to just do it on the graph, and then I'm going to just do it on the table. So we have 0, infinity, 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 infinity. Then we update all the adjacent vertices ones. So we have 0 plus 1 is equal to 1. So this is 1. We look at E. That one is going to be 3. 0 plus 3. So I'm no longer going to draw the addition there. I'm just going to say it out loud. So then we have the potential of A is 0 plus 7 gives us 7. 7 is less than infinity. So B gets updated to 7. Okay. Now we look at all our temporary ones and choose the smallest one and make that one a potential. So in this case, this is now a potential of 1. D, basically. Now we look at all the ones associated with adjacent to D. So we look at F. So we have 1 plus 3 gives us 4. 4 is smaller than infinity, so we update that one's temporary label. Then we look at E. So D has 1 plus 1. That gives us 2. 2 is less than 3, so we update E's temporary label to 2. There are no other vertices adjacent to D which don't already have potentials that we haven't looked at their temporary labels. So now we look at all the temporary labels and choose the smallest one. So we choose the smallest one, and that happens to be E, which is 2, so we update our 2 to now be our new potential. Then we look at all its adjacent vertices. So we go through the approach. 2 plus 3 updates our B temporary label to 5, because 2 plus 3 is 5, and 5 is less than 7. Then we also have C. So C is 2 plus 11. So 2 plus 11 is 13. 13 is smaller than infinity, so we update C's temporary label to 13. Okay? So once again, we look through everything and we select the one with the smallest temporary label. So in this case, it happens to be 4, which is by F. So if we do that, we've updated that one. Now we look at all the adjacent vertices to F, which are not potentials. There are none, so we don't have to do any math to update temporary labels. So we move on to the next vertice that has the smallest temporary label. So in this case, it's B, which is 5. So let's choose another color. So we update that one to its potential. Then we look at all the vertices associated with B, and can we update their temporary labels? We cannot, because there's none that aren't already potentials. So we move on to C, and then it becomes 13, where it has a potential. So then we have the answer now of the shortest distance from A to C is 13. Okay, now we're like, okay, but what was our path? So again, we approach it by our potentials and our weights. So in other words, you're going backwards now again. So we go, okay, 13 minus 11 is 2. So E is obviously something that we went along in our path. So we have C and E. Now we at E. So it has a potential of 2. So we look at the different options that we can go. We can either go to B, we can go to A, or we can go to D. So we say E. We have 2 minus 3 gives us a negative number. The number is not the same as the potential of A, so we clearly didn't go along that path, from E to A. We look at B, we have 2 minus 3, again gives us a negative number, so we clearly did not go along that path. So then we look at E, potential of 2 minus the 1, the weight of the edge from ED, which gives us 1. That one's potential matches the potential of D, so obviously we went along at that route. So we have D. Then again we look at all the different adjacent vertices to D to look at this approach. Eventually we say, okay, well, the potential of D is 1 minus the edge of AD, which is also 1, edge weight of AD, which is also 1, gives us 0, which means we travel from D to A. And that means our path is A, D, E, C. Okay, so let's do this one more time and let's use the table. Okay, so we're going to do this exact same example using the table. So we're still looking for D, A to C. So we have the table. So the table is going to have all the vertices listed, A, B, C, D, E, F. It's just going to have that situation. Here I'm going to write the paths to get there. So the first thing we do is we say, okay, we're starting at A, so we make A 0, all the rest infinity. Okay, so nothing new here. Then we look at all the ones adjacent to A and update their temporary labels if necessary, based on the rules. So we go through the process. So A is connected to B, so that one is going to be updated to 7. A is not connected to C, so you don't update that one. You don't have to write that line. I'm just doing that so you can see that I'm going through the approach. A is connected to D, and that gets updated to 1. A is connected to E, that one gets updated to 3. A is not connected to F. Now you look at all the temporary labels, and that includes, the C and the F, which is sitting at infinity, and select the one that is smallest. So in this case, it is D, which is 1. But before we move on, whenever you update your temporary label, update your path. So you updated B, so you started at A and you got to B, and that gave you a length of 7. So put that down so far. The same for the D, and the same for the E. Now you look at the temporary labels and update to their potentials. So you say, okay, D now becomes a potential. Now you look at all the adjacent vertices to D and you update their potentials accordingly. So is A connected to B? No, so you don't update that one. Is D connected to C? No, so you don't update that one. Is D connected to E? Yes, so you have 1 plus 1 gives you 2. 2 is less than 3, so this one gets updated. And now what you need to do is you need to update its path. It's no longer A to E, it's taking that path to D, so AD, and then it's adding E to it. So if you go ADE, you have a path of length 2. Whereas previously, if you went from A to E, you had a path of length 3. So you can see I'm just keeping track of the paths, or the shortest paths, as I'm going. Okay? Now we also look at F, because remember, we still need to finish all the temporary labels. So D, potential of 1 plus the weight of DF is 3, which gives us 4, so we update that one to 4. Now we look at all our temporary labels again. One thing, what did I forget here? I forgot to say that this goes from, again, you take the exact path to D, AD, you just copy and paste it, and then you add the F to it. Okay, now again, I'm looking at all the temporary labels, and I'm taking the lowest one. So in this case, I'm making E the potential. Okay, so E is now the potential. We now need to go through the process of updating all the adjacent vertices, if necessary, their temporary labels. So we go through the whole process. E is connected to B. So we have 2 plus 3 is 5. That is less than 7, so we update B to 5, which means we update its path. So we take the path that we have running in E at the moment, write that down, ADE, and then add the B to it. So now we know that ADEB is a path of length 5. Okay, then we move on. Continue updating our temporary labels. Is E connected to C? Yes, so let's go. Anything is going to be smaller than infinity in this case. So we have 2 plus 11 gives us 13. So we update its temporary label to 13. And we say, again, we take ADE and we add the C to it. Okay, we move on. D is already at its potential, so we don't care about it. We move on to F. Is F connected to E? No, so we leave its temporary label as is. Okay, now we select the lowest temporary label to be the new updated one. Here, that is 4, so 4 now, F becomes potential. Then we look at all the adjacent vertices to F. F doesn't have any adjacent vertices, so none of these get updated. So this one can't get updated, and this one can't get updated. The rest are all sitting at their potentials. So we're kind of done at that point. So we look for the next lowest. And in that case, it is B, which is 5. Now you'll notice I'm dragging it out. You don't have to have each one have a column situation. I'm just doing it to make it a little clearer to understand. So now we're sitting at B is 5, and we look at its adjacent vertices, which have temporary labels. There are none. So we kind of sorted. So we can't update C. C is the only one that has a temporary label left. So now we end up, and I'm running out of colors here, blue. Okay, we update this one here to 13. And the moment we do that, we have our D, A to C is equal to 13 because our C now has a potential. And we already have the path that it took, A, D, E, C. Okay, so one other thing to note, if I had to ask for the eccentricity of A, this method would work slightly better because I ask for all the paths in that direction because you can read the path straight away. But just again, going back to that, if I had to ask for you for the eccentricity of A, you wouldn't just stop at any vertex. You'll stop when you have no more vertices to switch from temporary labels to potential labels. And then you'll take the highest value for that one. In this case, C happens to be the one that is the last one with the potential, so the eccentricity of A here is 13.